Okay, so having studied and learned a little bit about the velocity ratio, let's consider the acceleration ratio. Now, with acceleration, the units are typically written as meter per second squared. So what would 1.25 meters per second squared mean? Does it mean we travel a meter each second squared? Well, a second squared doesn't really have any meaning, does it? So to understand the acceleration ratio, we need to unpack it a little bit and write it as follows. Meters per second per second. Now we can understand this. What happens? Each second, the velocity increases, so you're going faster and faster, by 1.25 meters per second. So it's a velocity increase of 1.25 meters per second each second. It's the velocity change over time. So, if you started at rest, then, with this acceleration, it would just go up by 1.25 each second. I'm not putting the units in here, but you get the idea. And if you were already in motion, this is like part B here. What I just did was part A. So here we're already starting at 2, and we just go up by 1.25 each second. So the acceleration is the same in these two cases, but here the acceleration happened when the object was already in motion, and in part A, the example, the object started off at rest. Now, acceleration does have direction, but it's difficult to visualize and interpret that, because it's easily confused with velocity. So as an example, let's imagine that we have an object that's accelerating to the east. Does that mean the object is actually traveling to the east? Well, no, it doesn't, right? Because the direction of the acceleration is not the direction that it's moving. For instance, okay, what if the object was moving in the westward direction and it was slowing down? Now, we're going to see shortly that if it's going west and slowing down, these two things together imply the acceleration is east. So the direction it's accelerating isn't the direction it's moving. It's the direction of the velocity change. Or, more simply put, the direction of the acceleration is the direction of the push. So we need to see how the velocity is changing in order to see which way it's being pushed. So as an example, let's say we have an object that's moving west and slowing down. The direction of motion, right, if it's moving west, motion, that's the direction of the velocity vector, okay? If this object is slowing down, though, which way are we pushing on it? Well, if it's going west and slowing down, we must be pushing on it this way. So the push must be opposite. The direction of the push, that's the direction of the acceleration. Try a few more examples. So here we've got an object that's falling. So that's the way it's moving. That's the direction of the velocity. And it's slowing down. To slow down, we must be pushing up on it. Maybe like a parachute's pushing up on it to slow it down. And that will be the direction of the acceleration. Okay, object moving east, so motion, that's the direction of the velocity, and it's speeding up. To speed up, we've got to be pushing it to the east, so that'll be the direction of the acceleration. You try this one. It's moving up and slowing down. Draw the picture. Okay, so pause the video. All right, so now what this would look like is this. It's moving up, the velocity's up. If it's slowing down, the push, which is the acceleration, must be in the downwards direction. Okay, here let's now consider the total flight of a projectile. So here we've got an object that's moving up and slowing down. So the acceleration of the push must be downwards. Then it starts to fall, So falling means the velocity is now downwards, and it's speeding up. Well, to speed up, the acceleration must be this way. So this is actually what a projectile does, right? In both cases, the push, or the pull of gravity, is downwards, opposite to the velocity, so it slows as you rise. Then on the way down, the velocity and acceleration are in the same direction, and it picks up speed. So hopefully that gives you some insight into the direction of the acceleration and how you can find it. So, well, this we did before. Let's just quickly sketch some graphs here. So this is an acceleration of plus 1.25 meters per second squared, or plus 1.25 meters per second. So if you start off at rest, example A, we did these numbers before on the previous page, then your velocity just goes up by the same amount each second. And that's just going to be a nice straight line graph starting at 0. So at 1 second, you're going at 1.25, then at 2 seconds, you're going as 2.5. Now, if in part B you were moving in the eastward or positive direction, it still goes up at the same amount each second. It's just starting not from 0, but from 2. And after 1 second, you're going at 3.25 meters per second. This y-axis is in meters per second units. And then after 2 seconds over here, you'd be at 4.5 meters per second. Excuse me. If you actually started off moving west as a vector, that is in the negative direction, as in the graph, that's going to correspond to being down here. Now what's going to happen each second is that your velocity is still going up by that amount. This means that you're going in the negative direction, but more slowly than you were before. So you're still negative on the negative side. This is negative 0.75. See if I can write that neatly enough. In the next second, now you've changed direction. You're going in the positive direction now. So the graph, here maybe I'll use the line tool. The graph looks like that. So somewhere in here, right there, the velocity reaches 0, which means that you actually stopped. In all cases, the acceleration's the slope, and in all cases, because these all had the same plus 1.25 meters per second squared, it'll be the same value for all of these graphs. Okay, so now, what does acceleration look like on, so those were velocity graphs, right, when we're accelerating. What about a position graph when we're accelerating? Well, let's look at this motion here. We're given a position graph, and there's 3 segments to it. So in the first segment, we see it's a nice straight line, positive, constant velocity. Let's call that section 1. So we saw that already. That's going to be not changing velocity. Actually, for reasons that will become clear shortly, just let me draw that line kind of down here a little bit more to give myself more room. And since the velocity is not changing, the acceleration will be 0. Or otherwise put, the acceleration is the slope of a velocity graph, and that'll be 0 here. Okay, here we have another straight line position graph, another constant velocity. This is segment 3 of the graph. It's still positive, it's still constant, but it's faster because it's a steeper slope than this segment was. So faster velocity, but constant. Constant velocity means no acceleration. Now, let me try and get a finer line here. What happens in this segment here? Well, we see it's curved. So the slope is actually changing. It's increasing. Now, if you look at the values, you see it's increasing from the slower speed, gradually increasing to the faster speed. So the slope value, that makes sense here, is gradually increasing, not right away, but over some time, increasing to this faster speed. So it's still a positive velocity, but it's changing. It's non-constant. So it's changing from a slower, more shallow line to a faster, which is a steeper line on the position graph. Okay, so now the acceleration, which would be the slope of the velocity, the rate of change of velocity, has a non-zero value and looks like that. Here's a graphing exercise for you to try. Now here we're given the velocity time graph, and we just want to answer some interpretation questions about it. So pause the video and try this one out. Okay, so first let's have a look at the interpretation. 3 sections, 1, 2, and 3. So this was, just like on sort of the middle section of this previous graph, this is a positive constant acceleration. We see this velocity is increasing from 0 up to a fast value. There's no numbers here, so it's going quick there. Section 2, we've got a negative slope here. That's a negative constant acceleration. So the direction of the acceleration is negative. That means we're pushing it in the negative direction. But the velocity numbers are still positive on this graph because we're still on the positive side of the axis. So we're pushing it left, but it's moving right. That means the object is slowing down. Right here, the velocity is 0. That means it comes momentarily to rest. In this third section of the graph, the acceleration is still negative. That's the slope. Now the velocity numbers are also negative. That means that we're pushing it to the left and it's moving to the left. Okay, for the quicker interpretation questions, where is the velocity the greatest positive value? Where is it going fastest? Right here. So I'll put a little b right there. When does the acceleration have the greatest positive value? All along here. That's positive acceleration, c, all the way along there. When is the position the greatest positive value? Well, that'll be when it stops and turns around. That'll be right here at this location there. So you can get a lot of information out of reading the graph. And these last few examples have shown you some of the tools that you'll use and some of the approaches.